Hello, my name is Alexis Engelke and I'll talk about practical binary optimization at runtime with LLVM. As we all know, performance is the main driver in high-performance computing. This applies for exploiting parallelism, but also the performance of sequential code is crucial. Therefore, compilers provide a wide range of program optimizations and transformations to improve utilization of available compute resources. In a traditional setting, the program is first compiled and then executed afterwards. However, in this setting, the compiler is unable to make use of runtime-only information. For example, the data layout may only be known at runtime and even dynamically change for load balancing, and also configuration options are typically only known after program startup. Yet, such information is helpful for optimization as it allows for removing indirections and more fine-tuned optimizations. It is generally impossible to generate all possible specializations at compile time, and for this reason, better performance utilization requires generation of optimized code at runtime. The simple way to just recompile the code on the fly with that information is no practical solution for HPC. It's not only that the compiler and the program sources may be inaccessible on the compute nodes, but also high compilation times would negate any performance gains. Therefore, our approach is to perform optimizations based on the compiled machine code. However, automatically determining which runtime data is actually constant is hard, as is predicting the potential performance impact. Thus, we rely on the application developer to provide explicit information about constant data and the code to specialize. We refer to this approach as application-guided optimization. Such an API-based approach has been previously explored by DBrew, a library for dynamically optimizing functions. With the DBrew API, function parameters and memory regions can be marked as constant, and DBrew generates an optimized version of the function. The main optimization possibilities in this setting are concept propagation, loop unrolling, inlining, and dead code elimination. DBrew performs only simple optimizations directly on the level of assembly code. Instructions with all constant input operands are removed and loops with a constant iteration range are unrolled completely. This is obviously a very fast optimization procedure, but operating only on assembly code with strictly local transformations also limits transformation possibilities. Also, DBrew's unrolling and inlining strategies may lead to a sizable amount of generated code. To address the problem of limited optimizations, we wrote a code generation backend for DBrew, which uses LLVM's optimizer and code generator. To do this, we lifted the assembly code produced by DBrew to LLVM-IR and used LLVM's JIT compiler to generate actual machine code. This improved the quality of the generated code, but it was still limited by DBrew's transformations, and the strict separation of lifting plus optimization in DBrew and optimization plus code generation on LLVM level prevents further transformations. For example, inlining an indirect function call whose address becomes only known during LLVM optimization. To avoid these DBrew-related problems, in our new approach we go directly from machine code to LLVM-IR. Here is an overview on our optimization procedure. We start with the machine code of the original function. We then lift the raw semantics of the machine code to an LLVM-IR function. For this, we reuse an existing lifting library, Reloom, which has a strong focus on performance. In the next step, we need to apply the calling convention to model function semantics at LLVM-IR level. This is necessary so that LLVM knows which parameters the function takes and what type they have, so that the new code has the same interface as the original code. After lifting, we can perform performance optimizations using standard LLVM passes, making use of additionally provided information about constant runtime data. The resulting code is then specialized to this configuration. Finally, we use the LLVM-MC JIT compiler to generate optimized machine code for the function and store it in the same address space, so it can be used instead of the original function. Before we go into the details of the lifting and optimization procedure, we will first go through a usage example of our library API. In this example, our optimization target is a simple function which computes the difference of two integer parameters. We now want to specialize the function for a constant subtrahend. To achieve this, we first need to create a new handle into the optimization library and specify the function we want to optimize. In this case, it's the function sub. we get back a configuration object where the optimization can be configured. Next, we need to specify the signature of the function. In this case, sub returns a 32-bit integer and takes two 32-bit integers as parameters. In future, this information may also be fetched from debug information sections like dwarf or CTF. Now we can specify our runtime knowledge. We can mark memory regions as constant or, as in this case, specify constant parameters. Here we specify the second parameter as a constant integer 42. After we finished our configuration, we can call bin.spec_create, which will perform the actual lifting and optimization of the function and will return a pointer to the optimized function. Note that the function has exactly the same signature as the original function. We can now call the optimized function like the original one, except that the optimized function will now use a different second parameter. Thus, the value of this will be 6 instead of 32, as it would be with the original function. Now we will go into the details of the optimization procedure. As the first step, we lift the raw machine code LLVM-IR code, which represents the semantics. For this, we use the lifting library Reloom, which was developed in the context of dynamic binary instrumentation. As such, it not only focuses on the performance of the lifted code, but also reducing the time required for lifting itself. The first part of lifting is to reconstruct the control flow of the function. This is done by following all direct jumps. The lifter stops either when we would leave the function, that is on a call to another function or a function return, or when it is impossible to continue, for example because of an indirect jump with an unknown target or an unsupported instruction. The result of this initial lifting is a single LLVM-IR function, which exactly models the semantics of the prior CPU instructions. This function takes a single parameter, which is a pointer to the virtual CPU state. This state contains the values of all registers, status flags, and also the program counter RIP, and is modified throughout the course of the execution. Now, to be able to generate a new function with the same signature and semantics, we need to do another lifting step. Therefore, we create a second LLVM-IR function, which has the same signature as the original function. This signature was specified by the developer using the API. In this function, we first make a stack allocations for a virtual stack, which must have a fixed size. This is necessary because naturally LLVM does not allow direct access to the stack. This size is application configurable as well and needs to be an upper bound of the potentially used stack space. We also stack allocate the CPU state structure and fill the structure with parameters according to the System 5 ABI and a pointer to the top of the virtual stack. Next, we add a call to the LLVM-IR function lifted by Reloom, which contains the function semantics. This call is inlined immediately afterwards to simplify subsequent optimizations. Finally, the return values are extracted from the corresponding registers in the virtual CPU state and returned. We note that the stack-allocated CPU state will in general be removed during optimizations by the scalar replacement of aggregates paths. For now, we only consider the code reachable by direct jumps. However, it can easily be the case that targets of indirect jumps or calls become known in the course of optimization. For example, this can happen when specializing for known callback functions, or when the function selects its implementation based on the known parameters. This is of course not predictable during the initial lifting process. Our solution to this problem was the use of a fixed point algorithm for code discovery. We start by initially lifting the code of the specified function, then we perform optimizations on this code. If we find jump targets with a constant address, we lift them as well and go back to the optimization step and repeat. We are done once there are no jump targets with a known address left. One benefit of our approach of rewriting machine code is the possibility to also go into shared libraries, even if their source is not available. However, initial experiences show that this is problematic for several reasons. First, high-performance rewriting requires that one is highly selective about the code parts that are rewritten, and several functions in shared library are usually not worth optimizing. There are complex functions with very few optimization opportunities, like functions for memory allocations or I/O operations. And some functions are highly optimized to the target architecture, containing even handwritten assembly code, where it is very unlikely that applying the standard LLVM code generator will result in a performance improvement. Examples of such functions are memcopy and memset in the C standard library. But there are also other problems. Many programs make use of lazy binding, where the target of a function call is only determined on the first call. Therefore, these addresses are stored in writable memory, which needs to be detected. Further, we must avoid lifting the dynamic linker itself, which is only called once and therefore no beneficial optimization target. In the light of these difficulties, we detect and avoid stubs in the procedure linkage table for now and do not optimize in the shared libraries. This is left as future work. Okay, now after having done the heavy lifting, we can now turn to the fun part, the actual optimization of code. In fact, we use a standard LLVM-IR pass pipeline with only minor modifications being required to be effective in the context of binary optimization. First, we add a new plugin for alias analysis, which marks all accesses to the virtual CPU state and any other memory region as no alias. We can safely do this because the original program doesn't even know that the virtual CPU state exists in the memory. This significantly improves the results of alias analysis and leads to much more optimizable and also idiomatic LLVM-IR code. Second, we add a new pass for propagating constant values from memory. In our context, it can frequently happen that the load instruction has a constant address, for example when it was specified as a constant parameter. This obviously doesn't happen when compiling code from source. Now, for such loads, we check whether the memory region for that address is marked as constant. If it is, we can just remove the load instruction and replace it with the constant. This pass is run multiple times throughout the pass pipeline. Third, we also need to add in pass to fold sequences of pointer-integer conversions to pointer arithmetic operations using the getElementPointer instructions. This allows for better constant propagation and alias analysis. Such a transformation could eventually be added to the upstream instruction combination pass as well. When lowering the resulting optimized LLVM-IR code, one problem can occur. It can happen that there are still indirect jumps where the target address could not be resolved. At this point, no further optimizations are easily possible. Therefore, we want to optimize as much as possible up to that jump and then continue execution at the original code. This incurs several challenges. First of all registers, including floating point registers, must have the values as they would have in the original code. Second, as we emulate a virtual stack inside the stack frame of the LLVM functions, also RSP must be modified to point to the top of the virtual stack instead of the real stack. And third, for the same reason, we must intercept the function return in order to set the stack pointer back to the real stack and clean up the stack frame of the LLVM function. We were able to solve these challenges by abusing the x86 interrupt return instruction iReadQ, which sets the instruction pointer and the stack pointer at the same time. For more details, we refer to the paper. Alright, we have now seen how we use LLVM for optimizing machine code. The question is, what's the benefit? To find an answer, we ran 3 benchmarks. The first benchmark is a micro-benchmark where the optimization target applies an arbitrary 2-dimensional sparse stencil to a 2-dimensional array. We specialize this kernel to a standard 4-point stencil and compare the execution time of the original code with our runtime optimized code. Additionally, we also compare against the compile time specialization of the code to the same stencil. The other 2 benchmarks are real-world operations from a widely used image processing library GEGL. We took 2 kernels. The first one is a 1-dimensional Gaussian blur filter, which applies a 1D stencil to an image. The stencil size and values depend on user configuration. The second benchmark is a bilateral filter, which applies a 2-dimensional stencil to an image. Additionally, this benchmark also has a more complex handling of the edges and corners in an image. Again, we compare the already optimized original code with applying our approach for runtime binary optimization. We don't compare against the compile time specialized code because the values we specialize for are user configuration and therefore never known during compilation. Here we see the normalized results of our experiments. For our stencil micro-benchmark, we can observe a performance improvement of 92%, including the time required for optimization itself. performed optimizations were loop unrolling, constant propagation, vectorization, and consequentially a better usage of instructions and registers. The runtime optimized code is even marginally faster when the code specialized during compilation for the same values. This shows that even optimization from binary code is able to achieve similar performance when a compiled time specialization. On the Gaussian blur filter, the overall performance improvement is 15%. Again, effective optimizations were constant propagation and loop unrolling, combined with fine-tuning of used vector operations. For the bilateral filter, the performance improvement is higher with around 33%, with similar optimizations being effective. We see that even optimized real-world code can significantly benefit from runtime post-optimization with further available information. Rewriting times are generally low in the range of 20 to 40 milliseconds, making only a small fraction of the optimized runtime. We also observe that the optimization time strongly depends on the code complexity. The resulting time for specializing on the 2D stencil of the bilateral filter is almost twice as high as the time required for specializing a 1D filter with the Gaussian blur filter. So we observed significant further performance increases with applying runtime optimizations, which are even profitable in already optimized applications. Generally, rewriting times can be considered as negligible, as long as the work is large enough, or the optimized can be used several times to amortize rewriting costs. However, the results also show that the optimization time strongly depends on the complexity of the code which is to be rewritten. Therefore, it follows that our technique must be used very selectively to code parts with a high optimization potential. Simply throwing it on large parts of a bigger application is very likely to result in a very long rewriting time, negating any possible performance improvements. To summarize, performance increases beyond traditional optimizing compilers are possible by using LLVM for runtime optimization of already compiled machine code. We showed how we reconstructed LLVM-IR from the raw machine code directly, so that it is possible to apply a standard LLVM optimization path sequence, which only required minor modifications to work effectively in the new context. Our approach also allows for a robust integration into existing code. If it is not possible to perform optimizations for any reason, it is always possible to continue execution with the original code. First experience with adapting real-world code shows that the cost for optimization can easily be amortized. As a next step, it would be highly beneficial to have tool support for estimating optimization potential. This could be a compiler reporting more actively on missed optimizations due to lack of information. Also, a system-wide infrastructure for caching rewritten code fragments can further reduce optimization costs, especially in HPC where multiple nodes could optimize the same code. This concludes the talk, and I'm happy to answer your questions.